So my thesis is entitled Multisensory Feedback to Enhance the Simulation of Walking in Virtual Reality for Rehabilitation. So the simulation of walking in virtual reality, or VR, is used in many applicative contexts. So this includes virtual visits, exercise games, vocational training, entertainment, and gait rehabilitation. However, because of limitations of workspace size and constraints related to fatigue, physical walking is not always available to simulate walking in VR. Therefore, simulations of walking in VR may involve other motions from the users, including walking in place, for instance, or cycling. And static users may even use simulations of walking in VR. And all of these examples diverge from real walking on several aspects. First, there is no self-motion from users, which means that they remain stationary. And these users do not perform walking movements in many cases, especially in the static case. And generally, the level of exertion required to walk in VR, it does not match the level of exertion of real walking. So in these cases, our objective is to enhance the simulation of walking in VR. And this means enhancing several aspects of user experience. Firstly, and most importantly, walking sensation, which refers to the subjective feeling of walking, but also embodiment, which relates to the relationship between the user and their self-representation in the virtual environment, or avatar. And specifically, embodiment refers to the feeling of owning, controlling, and being co-located with the virtual avatar. So ownership, agency, and self-location. We may also want to enhance vection, the illusion of self-motion in the virtual environment, presence, the illusion of being in the place depicted in VR, and that the events depicted are really occurring, and reduce cyber sickness, which corresponds to unpleasant symptoms caused by exposure to VR simulations. So our approach to enhance the simulation of walking in VR is to use multisensory feedback. And more specifically, we will consider several dimensions of walking, each of which we will simulate using feedback through one or several sensory modalities. So this includes vision, and visual feedback may take the form, for instance, of a walking avatar. Auditory feedback as well, with such as footstep sounds, and haptic feedback. So haptics refers to sensations of pressure, vibrations, and proprioception, which is the feeling of your body parts' position and motion in space. And haptic feedback may take the form of applying vibrations under the feet of the user, for instance. So more generally, the objectives of this thesis are first to explore these innovative techniques of multisensory feedback to enhance the simulation of walking in VR, and assess their effects on user experience during user studies. And in the longer term, we aim to apply our results to gait rehabilitation. So in this context, this thesis is a continuation of a project called Verare, which was started in 2020 by the Rennes University Hospital and INRIA Rennes. And this project aims to propose a VR-based tool for the gait rehabilitation of patients with neuromyopathy, which is a condition of the nerves and muscles caused by the immobilization and treatments during intensive care. And so these patients who are too weak to actually walk are immersed in VR using a head-mounted display. And in the virtual environment, they can observe from the first-person perspective a walking avatar, which you will see right now. And this allows to promote motor imagery, which consists in imagining being the author of the walking movement. Okay. So in the literature, walking has been simulated using several types of feedback that simulate various dimensions of walking. This includes body movements, self-motion, and physiological activity. And VR has been used for gait rehabilitation, which I'm also going to present. So the first dimension of walking that can be simulated in VR is body movements, which can be simulated using visual feedback in the form of a walking avatar, which can be presented from the first-person perspective or the third-person perspective. The use of a virtual avatar enables the sense of embodiment to occur, and when presented from the first-person perspective, it has been shown to increase presence and walking sensation. Haptic feedback may also be used to simulate body movements in VR. This includes the use of passive motion, electrical stimulation, or vibrotactile stimulation. Concerning passive motion, which will be a focus of this thesis, it has been shown to increase walking sensation. And outside walking stimulations, passive motion has been compared to active motion, and passive motion has been shown to induce similar levels of ownership while reducing agency. So in this context, the devices used for passive motion are quite complex and cumbersome, and the effects on embodiment are not known during walking simulations. So this will be the topic of our first contribution. Then the second dimension of walking that can be simulated in VR is self-motion, so the motion of the user in the virtual environment. And it can be simulated using optic flow. So optic flow is the result of the user's motion relative to the visual objects in the scene. Self-motion may also be simulated using what are called sound fields, which is the equivalent of optic flow, but for auditory feedback. So it corresponds to the relative motion of the user in a field of sound sources. And haptic feedback may also be used to simulate self-motion in the form of force feedback, airflow, or vibrations. So since contributions made in this thesis will focus on visual feedback, I'm going to elaborate on this point. So the first component of self-motion that can be simulated is global self-motion, which corresponds to the main trajectory of the user's body in the virtual environment. Several trajectories may be simulated, for instance, linear forward motion, rotating motion, or curvilinear motion, each of which are simulated using various types of optic flow and have been shown to induce several types of vection. However, this type of stimulation can also induce cybersickness, which is detrimental to a user experience. And the second component of self-motion that can be simulated in VR is what we call oscillatory self-motion, which refers to the periodic nature of the gait cycle and the left and right and up and down motion we perform while walking. And this can be visually simulated using what are called viewpoint oscillations. So here is an illustration. So these viewpoint oscillations may contain translations only, in this case, for instance, and they may contain rotations, translations and rotations in order to stabilize the center of the field of view. This is actually closer to real walking, since when we walk, our head and eyes rotate to stabilize our field of view. And more generally, viewpoint oscillations have been shown to increase vection, walking sensation, and presence. So in this field of research, viewpoint oscillations have been studied by several research communities and under various names. So this makes the discussion on the topic quite difficult. Moreover, it is unclear what are the effects of viewpoint oscillations on embodiment and cybersickness. And this stabilization of the field of view has only been implemented in immersive VR. So this led us to make two contributions, the second and the third. Finally, the last dimension of walking that can be simulated in VR is physiological activity. So since walking is a physical activity, it induces changes in the functions of the body, including, for instance, an increased or a more faster cardiac activity. So this can be simulated in VR using a heart shape or color in the peripheral vision, but also heartbeat sounds and vibrations applied to various parts of the body. Respiratory activity may be simulated using visual feedback in the form of avatar motion or colors in the virtual environment, or breathing sounds as well. And sweating and body temperature may be simulated using skin texture and color. Concerning the effects of cardiac feedback on user experience, it has been shown to increase perceived effort and to have a limited effect on heart rate, and to increase ownership, so a subcomponent of embodiment in some cases. Concerning respiratory activity, it has also been shown to increase ownership in some cases, and users tend to synchronize with the simulated breathing in VR. In this field of research, there is, however, a lack of multisensory approach, which means that the different sensory modalities are often used on their own. And these techniques have not been used to simulate walking, to our knowledge. So this will be the focus of a fourth contribution. Finally, VR has been used for gait rehabilitation. And in the case of several conditions, such as post-stroke, Parkinson's disease, and multiple sclerosis. And the VR-based exercises for rehabilitation rely on two main advantages of VR. The first one is that VR fosters motivation by immersing patients in playful environments. So these exercises may take the form of treadmill walking exercises, robot-assisted walking exercises, and balance training exercises. And the second advantage brought by VR for rehabilitation is that it provides visual feedback for action observation and motor imagery. So this is the case in the Virari project, as I explained you before, and for mirror therapy as well. So this is quite an open field of research, and there are new leads to explore, including the use of multisensory feedback, which will be the topic of a fifth contribution. So to summarize the contributions, we first focus on the simulation of leg motion with proprioceptive feedback. Then we focused on the simulation of head and eyes motion with visual feedback in the form of viewpoint oscillations. And we first conducted a systematic literature review on the topic, which led us then to make a technical and experimental work on viewpoint oscillations. And finally, we considered the simulation of physiological activity with multisensory feedback. And as a result of this technical contribution, we applied it to a clinical study where we, on the physical rehabilitation of long COVID patients using physiological feedback. Okay. So our first contribution is on the simulation of leg motion with proprioceptive feedback through passive cycling. So the context for this contribution was that, on one hand, repetitive movements are often judged strenuous to control walking. And on the other hand, some walking simulations do not provide any kind of proprioceptive stimulation. Therefore, our objective was twofold. We first wanted to reduce the required effort to walk in VR and to provide additional proprioceptive feedback. So our contribution was then to simulate leg motion with proprioceptive feedback through passive motion. And specifically, we chose cycling, since it was shown to be effective in controlling walking in a technique called walking by cycling. And this work, our work, resulted in a paper published to IEEE TVCG in 2023. So in this contribution, we developed a technique called assisted walking by cycling, which relies on a device for the passive motion of the legs. So it is a motorized cycling device called a cycloergometer. And to measure the cycling motion, we used a Vive tracker attached to one of the pedals. And then to control the walking motion of the avatar from this cycling motion, we use this following correspondence, where, for instance, when the feet of the user were horizontally aligned, it corresponded to the time of heel strike. To assess the effects of this technique on user experience, we conducted a user study where we compared three conditions. So the first one is condition assisted, which corresponds to our technique. So here you can see the legs of the user, which are driven entirely passively. And you may also see the use of a first-person perspective avatar. We compared this first condition to a second called active, in which the user had to actively cycle to walk at the same pace as the previous condition. and a last condition without any proprioceptive feedback, where the user did not move their legs. And this study was conducted using a within subjects design with counterbalanced ordering of the conditions. So concerning the results of this first study, it showed that both conditions with cycling motion induced more walking sensation than the static condition, but we found no significant difference between the two conditions with cycling motion. So this shows that our technique renders quite a compelling walking experience. Then we considered perceived effort and perceived fatigue as well. And the analysis, the statistical analysis showed that the active condition induced the strongest level of perceived effort, then the assisted condition, and then the static condition. But we found no significant difference regarding perceived fatigue, which is probably related to the rather short duration of the conditions. And more generally, this shows that our technique could indeed reduce the level of perceived effort compared to active motion. Finally, we considered the sense of embodiment as well, and found that both conditions with cycling motion induced more ownership than the static condition. And we found the active condition to induce the strongest level of agency, then the assisted, and then the static condition. So this confirms previous work conducted in the field on the comparison between active and passive movements. And it shows also that our technique induces good levels of both ownership and agency. So to conclude on this first contribution, our objective was to reduce the required effort to walk in VR while providing proprioceptive feedback. So we designed a technique called assisted walking by cycling for the passive cycling motion of the legs during walking simulations in VR. And we conducted a user study that showed we could indeed reduce perceived effort compared to active motion and enhance user experience compared to no motion in terms of walking sensation and embodiment. And this may have applications to gait rehabilitation on patients with severe fatigue who may benefit from this additional proprioceptive feedback, or replace the use of motorized cycles which are already in use. Okay. So the second dimension of walking that we considered in this thesis was the motion of the head and eyes, which we simulated using visual feedback. And this consisted first in a systematic literature review on the topic of viewpoint oscillations. So the context for this contribution was that viewpoint oscillations had been studied by several communities, including VR, human-computer interaction, and vision, and under different names. So this made the gathering of information on the topic quite difficult. And we also, their effects on cybersickness and embodiment were unclear to us. So this is why we conducted this systematic literature review. And we had several objectives. First, clarify the terminology, describe past implementations, synthesize the results regarding their effects on user experience and cybersickness and embodiment specifically, and discuss the perspectives for future research. And this resulted in a publication to IEEE TVCG in 2024. So in this contribution, we defined viewpoint oscillations as periodic changes in position and or orientation of the point of view in a virtual environment. And we gathered 44 studies on that assessed their effect on our metrics of interest of user experience. And the main takeaway messages were that they increase vection. So this is supported by a large number of studies. They also increase walking sensation and presence, but the level of evidence is a little bit lower. We found mixed results on cybersickness, so both positive, negative, and non-significant. And we found a single study regarding their effects on embodiment, which showed rather detrimental effects. So for more detail on this contribution, please refer to the manuscript. I'm now going to present the third one, which is a technical and experimental work on viewpoint oscillations. So this contribution was made because of the perspectives we identified in the previous one. and which were that we had little knowledge on the effects of viewpoint oscillations on the sense of embodiment, and that mixed results had been found for cybersickness. And concerning their implementation, no stabilization of the field of view with rotations had been done in immersive VR. So our contribution was to implement a stabilization of the field of view with gaze tracking based rotations in immersive VR, and conduct a study on the effects of standard viewpoint oscillations and stabilized viewpoint oscillations regarding walking sensation, embodiment, and cybersickness. And this was submitted to IEEE VR 2025. So to simulate natural viewpoint oscillations, we first considered the translatory component of the oscillations, and we opted for a trade-off between the naturalness of biomechanics and the predictability of simple model-based formulas, such as sinusoidal functions. So what we did was base a formula on the results of a study on the biomechanics of head motion during walking. And so this is the resulting formula, which I'm not going to detail, but here is the resulting translations along the three directions of space. And here is maybe a more visual representation of the pattern of oscillation viewed from the back, the top, and the right. To increase even more the naturalness of the oscillations, we implemented a stabilization of the field of view with rotations. So the stabilization process followed three main steps. First, we applied the translation to the viewpoint or the camera. Then we scanned the virtual environment to find the target of the gaze. So we first fetched the direction of the gaze from the gaze tracker in the head-mounted display. We found the gaze target. And then the third step consisted in applying rotations to the camera so that the gaze target, the gaze direction would be aligned with the gaze target previously found in this new camera's position. And over time, this resulted in a stabilization of the field of view, whereas without this process, the gaze target would oscillate in space. So to assess the effects of this technique and of viewpoint oscillations in general regarding embodiment and cybersickness, we conducted a user study that compared three conditions. So here is the first one. Nothing much to see because it's just a linear translation of the viewpoint in space. Then we compared this condition to a condition with oscillations but no stabilization. And you may see that the green dot, which represents the target of the gaze, oscillates in space because there is no stabilization of the field of view. And the third condition was the oscillations plus the stabilization technique. And you may see that the green dot is stabilized in space, but the peripheral field of view still moves. And once again, we used a within subjects design with counterbalanced ordering of the conditions. So the results of this study showed that both conditions with viewpoint oscillations increased walking sensation, but there was no significant difference between the two conditions with oscillations, so stabilized and unstabilized oscillations. So this shows a benefit of viewpoint oscillations in general, but no benefit of using the stabilization technique. We also considered cybersickness, but found no significant difference between the conditions. And this is clearly related to the rather small level of cybersickness overall in the experiment. And concerning embodiment, we found an increased ownership in the stabilized oscillation condition compared to the linear condition, and no significant effect on agency. So this actually contradicts the previous study that we identified in the literature. And according to our results only, it suggests a rather positive effect of viewpoint oscillations. So to conclude on this third contribution, our objective was to simulate the motion of the head and eyes during walking in a natural way with viewpoint oscillations. From a technical standpoint, we designed natural translations of the viewpoint and a stabilization of the field of view with gaze tracking based rotations. And we conducted a user study which showed that viewpoint oscillations can enhance user experience regarding walking sensation, ownership may be also enhanced, and we found no significant effect on cyber sickness. Moreover, the study showed that our stabilization technique was feasible and that it performed at least as well as traditional viewpoint oscillations. And so this technique could be applied to many walking simulations, and especially for gait rehabilitation. Okay. So the last dimension of walking that we considered in this thesis was physiological activity, which we simulated using multisensory feedback. So the context for this contribution was that many walking simulations do not match the real physical exertion of walking, and this can be simulated in VR using physiological feedback. And interestingly, this has not been done in past work, and physiological feedback has been used in other applicative contexts. And in general, there is a lack of multisensory approach in this domain. And specifically, no haptic feedback has been yet proposed to simulate respiratory activity. So our contribution was to design multisensory feedback to simulate both cardiac and respiratory activity during walking in VR, and to conduct a series of user studies to assess the effects of this feedback on perceived effort, walking sensation, and embodiment. And this was published to IEEE TVCG in 2022. So first, to generate the physiological activity corresponding to a walking avatar, we designed a physiological model that took into account the avatar's physical traits, including height, weight, and gender, and the characteristics of the virtual exertion. And this model then computed in real time the change in respiratory activity and cardiac activity with a list of 4 parameters. And generally, these parameters dictated the frequency of the feedback and its intensity. So we designed 3 sensory modalities to represent both respiratory and cardiac activity. For respiratory activity, we used a vapor cloud for visual feedback, a breathing sound for auditory feedback, and we designed a compression belt for haptic feedback, which is illustrated in this video. So you may see here a motor which spins to wrap an elastic band around the waist of the user. And this delivers a pressure stimulation which during the simulated inspiration, which is synchronized with the other sensory modalities. And here is a visualization from the first-person perspective. So you can hear the breathing sounds. You see the breathing cloud as well, the vapor cloud. And it may be harder to see, but the belt is also active. And with the 3 levels of slope, you can see also that the simulated activity increases in frequency and intensity. Then, concerning cardiac activity, we also designed 3 sensory modalities. So for visual feedback, it consisted of this gray color in peripheral vision. For auditory feedback, we used the heartbeat sound, as you can hear. And for haptic feedback, we applied a vibration to the user's wrist, which is hard to put into pictures, but it is consistent with the other 2 sensory modalities. So to evaluate these techniques, we conducted a series of 3 user studies. The first one was dedicated to evaluate each sensory modality of the respiratory feedback. So we compared in this first study 5 conditions: a condition without feedback, with visual only, auditory only, and haptic only, and multisensory feedback. The second study was followed the same design, but for cardiac activity. And the last study was dedicated to assess the effect of combining the two multisensory feedbacks. So we used multisensory respiratory feedback, multisensory cardiac feedback, and a combination of the two. So in all three studies, we used a within subjects design, once again, with counterbalance conditions, and the participants in the study were not the same. So concerning the results, we found an increased perceived effort using our techniques, but only in the multisensory condition. So this was the case in user studies 1 and 2. And in user study 3, we found also an increased perceived effort in the combined condition compared to the cardiac condition. We also assessed walking sensation, but this time found no significant difference. So this shows that while the simulated physiological activity was related to the walking activity of the avatar, it did not have our feedback did not have an impact on the subjective experience of walking. Concerning the sense of embodiment, we only found a difference between some of the conditions and the control condition in user study 1, where for two subcomponents of the questionnaire we used, namely appearance and response, we found an increased value in the multisensory condition compared to the control condition. So this suggests some benefits of the respiratory feedback regarding embodiment. In the same study, the first study, we also measured participants' breathing, and we computed the difference between their breathing and the simulated breathing, which showed that, especially in the multisensory condition, users tended to synchronize their breathing with the simulation. So to conclude on this fourth contribution, our objective was to simulate the changes in physiological activity related to walking in VR. So from a technical standpoint, we designed a physiological model to generate the physiological activity based on the avatar's traits and the walking activity of the avatar. We also designed 3 types of sensory feedback for both cardiac and respiratory activity in VR, which implied designing this compression belt for the feedback of respiratory activity. And we conducted a series of user studies, which showed overall an increased perceived effort when using our feedback, but no effect on walking sensation. And the studies also showed that our respiratory feedback induced a synchronization of user breathing and may also benefit the sense of embodiment. For future applications of this technique to rehabilitation, since our technique have an effect on perceived effort, they may be used during physical rehabilitation. And this is the subject of our 5th contribution on the physical rehabilitation of long COVID patients using physiological feedback. So first, what is long COVID? Well, long COVID refers to symptoms that 10 to 15% of people show more than 3 months after an infection by SARS-CoV-2, which is the COVID-19 virus. And these symptoms include symptoms of fatigue and intense perceived effort. Studies have recommended using physical rehabilitation in this population, some of them using VR. And so our objective in this context was to use our feedback of physiological activity to influence these patients' perceived effort during sessions of physical rehabilitation. And this resulted in a paper which is accepted as a letter to the editors in Annals of Physical and Rehabilitation Medicine. So as the type of exercise we chose for physical rehabilitation, we chose cycling, since it was used in past studies on physical rehabilitation of long COVID patients, and since it's rather safe to use when immersed in VR. And to achieve our objective of manipulating perceived effort during these rehabilitation sessions, we used our simulation of respiratory activity with different rates of simulated breathing. Specifically, we compared 3 conditions, a condition called slow, a condition called neutral, and fast, which respectively corresponded to a slower simulated breathing than the participants' breathing at the same level of exertion, a neutral breathing rate, or a faster breathing rate. And in the virtual environment, we once again, we this time used simulated a cycling exercise, and this was done so that participants would not be disturbed by the use of VR, which they were not used to using. And once again, we used a within subject design with counterbalanced ordering of the conditions. So the results of this study regarding perceived effort and fatigue were, however, negative. So we could not find an effect on perceived effort and fatigue between our different conditions. However, we found a strong effect of fatigability, which means that throughout the rehabilitation session, only one, they were more and more fatigued as it went on. We measured breathing rates as well and found that the condition with faster simulated breathing rates increased participants' breathing on average. So this shows that our feedback could influence their breathing rates. We were also interested in the effects of our feedback on the sense of embodiment, and we expected the condition with the most accurate breathing rate, simulated breathing rates, to yield stronger levels of embodiment, but we did not find such an effect, as the conditions did not significantly impact any subcomponent of embodiment. We conducted additional analysis on this data. The first one was dedicated to remove this effect of fatigability by considering only the first condition. So we only considered the first condition of each participant, but this did not yield any additional results. And we conducted another analysis by splitting the population in 2 based on the intensity of the participants' symptoms. And we found that the most deconditioned patients, so the patients with the most intense symptoms, seemed to prefer the condition with slower simulated breathing. So to conclude on this 5th contribution, our aim was to manipulate non-COVID patients' perceived effort during physical rehabilitation using physiological feedback. So we conducted a study that aimed to see whether simulating different breathing rates would affect their perceived effort, but we could not find an effect on perceived effort or fatigue. Still, we showed that our techniques could influence their average breathing rates, and that the most deconditioned patients could seem to prefer the slower simulated breathing. And overall, participants appreciated using the system, which is quite promising for maybe future studies using the same feedback. And concerning these future studies, we would like to conduct additional studies by comparing the use of our feedback to not using any, which may yield more positive results. So to conclude on this presentation, I'm first going to summarize the contributions. So first, we simulated leg motion with proprioceptive feedback, and we designed a technique called assisted walking by cycling for the passive cycling motion of the legs during walking simulations. We conducted a user study which showed that this technique could reduce perceived effort compared to active motion and enhance user experience compared to no motion. Then we considered the motion of the head and eyes with visual feedback. And this led us to make a systematic literature review on the topic of viewpoint oscillations, which synthesizes their effects on user experience. We designed a technique for stabilized viewpoint oscillations in immersive VR, which we assessed in a user study that showed that in general, viewpoint oscillations may enhance embodiment and have no effect on cybersickness. Finally, we considered the simulation of physiological activity with multisensory feedback, we designed 3 types of sensory feedback for both cardiac and respiratory activity, and conducted a series of user studies that showed this feedback could increase perceived effort. And we conducted a prospective study on the physical rehabilitation of long COVID patients, which showed mitigated results. So this work opens perspectives for future research. First, concerning assisted walking by cycling, this technique could benefit from providing more control to users, since in our evaluation, participants did not have any. And future experimental work on this technique could also investigate the quite high level of perceived effort that we identified in the study. Then we, for concerning viewpoint oscillations, we should investigate their effects on the sense of embodiment further, since we found results that are contradictory with the single other study conducted on the topic. And we also worked on the design of another technique of customization of the viewpoint oscillations, which I didn't have time to present today, which we would like to evaluate in user studies in future research. Concerning physiological feedback, our model could benefit from including measures of the user's actual physiological activity to adapt the simulation to the user's activity. And this should be evaluated in future research. And concerning its clinical use, we would like, as I said at the end of the last contribution, we would like to compare the use of our feedback to using no feedback. And finally, there are technical perspectives we would like to explore in future research. For instance, implement variations for turns, since we only considered walking on straight paths, accelerations as well, slopes and ground materials. Concerning further experimental work, other dimensions of user experience may be explored, including vection and presence, which we considered only in the systematic literature review, and other dimensions as well, including usability and workload, for instance. Other tasks during user studies may also be considered, such as navigation, interaction tasks, or spatial cognition tasks. And our techniques could be applied in the future to rehabilitation. So concerning walking by cycling, as I mentioned, it could be used in intensive care, such as like in the case of Verare. And it could also be used as an alternative to robot-assisted walking, which relies on complex devices. And concerning viewpoint oscillations, they could be used in any walking simulation, including during rehabilitation, provided that there is no effect on cybersickness, which should be checked in future research. So this concludes my presentation, and I thank you very much for your attention.